doing this video to help you understand what a sampling distribution is. Illustrating a sampling distribution. First, if you were to create a sampling distribution, you would obtain a simple random sample of size n from your population. You compute the sample mean of that. Okay, if this is the sampling distribution of the sample mean. You you compute the mean of that particular sample. Then, assuming we are sampling from a finite, which means there's a set number in your population, there's not like infinitely many things in your population, you would repeat steps 1 and 2 until all simple random samples of size n have been obtained. So every single combination of n objects in that sample, in that whole entire population, we would get that sample and we would find the mean of it. And we report it down. And then when you're done doing all of those, recording down each one of those sample means, then you would simply tally up how many of the samples had a mean of 50, how many samples had a mean of 40, how many samples had a mean, and you would do a distribution, a frequency distribution of how often each different sample mean occurred. And that's what we call a sampling distribution of the sample mean. Here's an example. The weights of pennies minted after 1982 are approximately normally distributed with mean 2.46 grams and standard deviation of 0.02 grams. So this is the distribution of the weights of the pennies. This is what I often refer to as the original distribution or the population distribution. This is when we first get introduced to normal distribution, this is often what we're finding. We find the probability of finding one particular penny having a certain weight, and we use the area under this curve of the original population to find the probability of a certain penny being a certain way. So that's our original distribution or population distribution. So there's the distribution of pennies. I drew it out for you here with the mean in the middle of 60. Oh, it should be 2.46. Sorry, I don't know why I put 60. This 60 right in the middle of your distribution should be 2.46. Okay. Approximate the sampling distribution of the sample mean by obtaining 200. So we're going to do an illustration, and we're going to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size 5 from this population. So they find the first sample of size 5, and the first weight of that penny was 2.493. The second weight of the second penny in the sample was 2.466. The third weight was 2.473. The fourth weight was 2.492, and so on. Those are the weights of the 5 pennies in a sample. They found the average weight of the sample, which is the mean weight, and is the sample mean, which we also call X bar, was 2.479. Okay, so then that was for sample number 1. Now there's 199 more because there's a total of 200 samples. And they did that again 199 more times for all those other samples, and they calculated the sample mean of each one. Here are the sample means of each of the 200 samples. Now they did a frequency distribution to see how often each of these sample means came up. And the mean of those 200 sample means, so the average of the sample mean, which is kind of weird, we're saying sample mean of the mean, is also 2.46, which was actually the average weight of the original population of pennies, of just the weights of pennies, individual pennies by themselves. The standard deviation of the sample means they calculated, and it's 0.0086, which is much smaller than the standard deviation of the original population. If you remember, just a few minutes ago, we saw the standard deviation of the original population is 0.02, and now the distribution of the sampling and the sample mean is 0.08086, so it's quite a bit smaller. So here is the histogram. Just like I said, they're going to take those individual sample means from each of the 200 different samples that they did, and they're going to do a histogram, which tallies how many of them had 2.4, how many of them were between 2.4 and 2.5, how many of them were between 2.5 and 2 and 3. And so they do that. Here is the histogram. And actually, you see that most of the sample means, when they took a sample and they found the average of that sample, most of them were coming up. The high rectangle there is in the middle. It looks like between 2.455 and 2.465. So that would be 2.45, right? It looks like around that value. I'm sorry, 2.46 is about right in the middle. There is the average of these, and they already said that. They already told us in the previous screen, the mean of these means is 2.46, right? 2.46, right for that. Okay. So this is the distribution, is the sampling distribution of the sample mean. Along the bottom here are the sample mean weights, and their frequency is on the side here. And then a lot of times they'll use this X bar notation because the random variable along the bottom here is the sample mean, and it's not just one individual value here, so of X, but it's the sample mean of X. So that's a difference between these two distributions. So here's from a previous chapters, and I don't know, I put 60 here. Should fix it where we see 60 should be 2.46. But anyways, the original distribution that we studied in, I think it was chapter 7, or maybe it might have been chapter 6. But one chapter we studied just normal distributions. So we just studied the population distribution on top. And they gave you a mean and they gave you a standard deviation. Those are the ones you use to make your calculations. And the mean and standard deviation here was always given to you in the problem. Now they're going to be asking questions about the probability of a sample happening and occurring. And when they give you that, you have to find the sampling distribution. And the mean of that distribution is equal to the mean of what I call the original population, or the population distribution. And that's what this notation here means. And the standard deviation of this sampling distribution, by studying it and by doing this, doing simulations, they figured out that the standard deviation of the sampling distribution is equal to the original standard deviation of the original population, which is usually given to you in the problem, divided by the square root of the sample size that they tell you that they took. So that is our equations that we're going to have to use to find the mean and standard deviation of the new sampling distribution. Just so that you know, when an original distribution is normally distributed, the sampling distribution is normally distributed as well. But it's a lot narrower because, like we said earlier, the standard deviation is smaller. So you can look at the notice the differences between what the original population there looks like and what on the bottom, the sampling distribution, the corresponding sampling distribution would look like if you had size 30, a sample size 30. If you had a smaller sample size, then you would probably have it would be a little thicker and it wouldn't be quite as tall, but it would be thicker. So it's somewhere in between these two pictures. So the top picture is what you were dealing with in, I believe it's chapter 7, and then the bottom picture, I believe it's chapter 8. They're always asking about probabilities of a sample occurring. Then you have to use the mean and standard deviation from the sampling distribution. If they're asking you about a single thing, there's a probability of a single penny having a certain characteristic, then you have to use the original population distribution that's on the top here. And so just in conclusion, summarizing everything, the sampling distribution of the sample mean, they're going to tell you that it's that distribution by putting an X bar along the X axis there. Notice the little X bar along the X axis. And I don't know if I emphasize that. Okay. And then if they're talking about the original population, they just put an X along the X axis. But the sampling distribution of the sample mean is simply the probability distribution of this of the sample mean, meaning that it gives us the probability of having a sample with a certain characteristic. And the area under this curve gives us the probability of a sample being less than 35 or whatever it is. And notice here that the area under this curve is 1 because every single possible different sample is sample mean. Every different possible sample mean is represented here, and the probability of each one of those occurring is given. All right. I hope you found this valuable. Have a great day. Bye.